This video will look at some of the tools used by scientists, specifically focusing on some of the different types of microscopes, and then the metric system and how we convert between the different measurements in the metric system. So here we have the compound light microscope. This is the one that we would use in class. And with microscopes, we talk about two things typically in terms of like how good they are. The first is magnification, which for the compound light microscope is determined by multiplying the amount that the eyepiece magnifies the object times the amount that the objective or the lens magnifies the object. So the eyepiece magnifies 10 times, and the lowest power objective magnifies 4 times. So if we multiply that, 10 times 4 is 40. So the total magnification with the lowest power objective in place is 40. The medium power objective is magnifies 10 times. So total magnification with that one is 100. And then the high power objective magnifies 40 times for a total magnification of 400. So that's how we determine magnification, which is of course how much bigger the object appears than it is in reality. And then the second measurement that we use, or the second definition in terms of how good a microscope is its resolution. And the resolution is the ability to distinguish between two objects. And what that means is if you have two things and they're this far apart on the slide, and you can distinguish that those are two things versus just one blob, the resolution is the measure of that distance between the two objects. So the closer together two things are, and we can still tell that they are two things, that's a measure of a good quality microscope. So for compound light microscopes, what you have is light that passes through the object. As you can see on this picture here, sometimes the light is a lamp that supplies the light, and then sometimes the microscope will have a mirror that simply redirects the light from the room. You would not want to use a microscope that utilizes a mirror as a light source outside. You don't want the sun to be your light source because you don't want to be shining light from the sun directly into your eyeballs. The ones we have are the ones with the lamp that provides its own light source. And then magnification of compound light microscopes, the max is 1,000 times. So some of the nicer ones that we have here at school do have a fourth lens that magnifies 100 times for a total magnification of 1,000. But most of the ones that we use in here will be the ones that max out at 400 times magnification. And then the resolution of these microscopes is up to 500 nanometers. So nano, we'll talk about in a little bit, is 1 billionth. So imagine taking a meter stick and cutting it into a billion pieces, put 500 of those billion pieces side by side, and that's 500 nanometers. And that's how close two objects can be and still be distinguished as two separate objects. So that's pretty decent magnification. And we'll be filling in a picture diagram of a microscope later to learn the different parts. So we'll do that in class. So this is a typical image that you would get from a compound light microscope. This is a human skin cell, probably a cheek cell. And you really can't identify specific cell parts other than the cell membrane and the nucleus. So we don't get very detailed images with a light microscope, and it has to be something that's small enough and thin enough for light to pass through. Otherwise it just looks like a dark blob on the microscope. So a fancier version of a microscope would be like a transmission electron microscope, or a TEM. And this passes, rather than a beam of light, it passes a beam of electrons through the object. And those electrons are going to be focused using magnets, whereas on the compound light microscope, the focusing happens using mirrors. So electron microscopes use magnets. Unfortunately, only dead cells can be viewed because they have to be embedded in plastic and then sliced super, super thin in order for the electrons to pass through. But it does give you much greater magnification. I don't have an exact number, but I've seen 10,000 times or more magnification, so much higher than the light microscope. And the resolution is also better, 0.2 nanometers, so less than one of those billion pieces of the meter stick. So because of the greater magnification, we get much more detail. You can see this picture says that it is magnified 15,000 times. So much, much greater magnification and therefore much greater detail. So now not only can we see the nucleus, but we can see mitochondria, we can see endoplasmic reticulum and Golgi apparatus, so much, much greater detail in the pictures with a transmission electron microscope. Scanning electron microscopes are similar to transmission electron microscopes in that they both use electrons, but rather than passing the beam of electrons through the image or object, we're going to pass it along the surface of the object. And what that's going to do is generate a three-dimensional image. Slightly less magnification than the TEM, and I have not seen resolution information for the SEM. But I would imagine it is still better than the light microscope. And I've also seen conflicting data as to whether or not it can be used with living cells. Some sources say yes, some say no, so I'm not sure what the answer to that question is. But the advantage of the scanning electron microscope is being able to see the surface of something. We had not been able to see the surface of a cell prior to the invention of the scanning electron microscope. Now, both electron microscopes are way too expensive for a high school to own. I have heard of organizations that will loan scanning electron microscopes to schools, but I have not been able to get access to one of those. But these you would primarily see at major universities or research institutes. So here you see some human cells. These are blood cells, both red and white blood cells. And you can see that you get that three-dimensional image of the surface. So we're not going to see the nucleus in a scanning electron microscope image, but we'll see the outside of the cell. All right, so in science, we use the metric system or System International or SI system for our measurements. And we do that for multiple reasons. One, it's based on the number 10, which is a whole lot easier than the system we use here in the US. In the US, we've got feet and inches and all this stuff, so it's 12 inches in a foot, 3 feet in a yard. I don't even know how many yards in a mile. So there's not a consistent scale that's used in our system. So it's much easier to use the metric system, which is based on tens and multiples of 10. Much, much easier to convert between different units. It's also universally understood. It's used worldwide by scientists. So if I take measurements here in the US and I send that data to somebody in France, they're going to understand it without having to worry about converting it to a different system. So scientists around the world use the metric system, and that just makes life a whole lot easier. So our metric units for length, we measure in meters. Mass is measured in grams. Volume of a liquid is measured in liters. If it's a solid, it's usually going to be in centimeters cubed. Time is in seconds. And then temperature is typically either in degrees Celsius or Kelvin. By the way, it's not degrees Kelvin, it is just Kelvin. And if you didn't already know this, absolute zero is 0 Kelvin. And as far as I know, we have not achieved absolute zero. Absolute zero is the point at which all molecular movement would cease. And I don't think they've gotten the temperature that low yet to actually achieve absolute zero. All right, so with the metric system, we use prefixes to indicate the size of something. So to the left of the basic unit here, and the basic units would be what we just talked about, meters, grams, liters, seconds, etc. But everything to the left here is going to be bigger, and everything to the right is going to be smaller. And the easiest way to do this is, as it says here in the instructions, is to move the decimal point in the direction that you are moving along this chart. We're going to do some practice with this in just a second, but wanted to point that out to you. So as I said, we'll practice this in just a second. Hopefully this will make more sense. But the easiest way to convert in metrics is to just move the decimal point. All right, so I'm going to write my metric prefixes, just abbreviations for them along the top here so that we can see the direction that we're going to be moving. So you've got King Henry died by drinking chocolate milk Monday night. And DECA, by the way, is DA. And then micro is this little weird U looking thing called the mu. It's a Greek letter. So that's how you tell those apart versus deci and milli. So I just wanted to point that out. So now B here is our base unit. That's where we're going to kind of start from for a lot of these. But between each of these, you're going to move one decimal point in that direction when you're doing the conversions. Except down here between milli and micro, we're going to go 3 decimal places because we're going from 1,000th to 1,000,000th, which is 3 additional zeros. And then between micro and nano is another 3 decimal points. So I like to write that on my paper by saying King Henry died by drinking chocolate milk Monday night. That way I can see exactly where I need to move my decimal point, what direction, and how many places. All right, so let's start with 2,000 milligrams, and I want to know how many grams that is. So we're going from milli, which is right here, to grams, which is our base unit. Whoops. There we go. All right, so we're going to the left, and we're going to go 1, 2, 3 places to the left. All right, so my decimal right now is right here at the end, and I need to go 3 to the left. So I'm going to go 1, 2, 3, and now my decimal is right there. So 2,000 milligrams is 2 grams. Okay. So now let's do another one. I've got 104 kilometers. I want to know how many meters that is. So this time, let me see if I can change color. I tried and it wouldn't let me. Try this. We're going to go from kilo to meter. So we're going to go 1, 2, 3 to the right this time. So again, my decimal point is here at the end, and I'm going to go 1, 2, 3, and I have to fill in with zeros. So I have 104 and then 1, 2, 3 zeros. So 104,000 meters. So we'll get more practice with this later in the unit, but this hopefully just kind of shows you what I mean about moving in a particular direction on the metric conversion chart here, and knowing the direction and how many places to move the decimal point.